Hello, welcome to another module in this massive open online course. So, in this module, let us look at a very important and interesting application of the concept of positive semi-definite matrices and eigenvalues, and that is in the context of PCA or principal component analysis, which is a very important concept in machine learning. Alright, so we want to look at the application of positive semi-definite matrices and their eigenvectors. This is termed as PCA, which stands for principal component analysis stands for principal component analysis, and this is one of the most important concepts in ML, that is machine learning. We have already seen an application in machine learning, that is using the Gaussian classifier. This is another important application of linear algebra, that is principal component analysis. And what this is roughly, essentially, when you have the data vectors x bar I, which are very high dimensional, for example, one can think of facial images, right. So, let us say you have facial images which are, for instance, 256 cross, even you can consider a typical image of size 256 cross 256 pixels, and which is basically an image of size 256 cross 256. So, if you make this a vector, then it will be a vector of size. So, from this, if this facial image, if you make this a vector of pixels, this will be a vector of size 256 square cross 1, right. So, if you take the pixels of the image, put them column wise, this 256 cross 256 image, it will be a vector of size 256 square cross 1, that is 2 to the power of 8 square, 2 to the power of 16 cross 1. So, you can see it is a very large vector, which means the data is going to be multidimensional and dimensionality is very high, right. So, if you look at this machine learning application, so the dimensionality can be very high. Not just very high, it is extremely high. So, when the dimensionality is very high, right. So, high dimensionality this implies that the analysis or the analyzing the data is going to be highly difficult. So, when you have data of very high dimensionality, the analysis of data is going to be very difficult, and therefore, this high dimensional data has to be compressed, right. You have to reduce the dimension of this high dimensional data. This is known as dimensionality reduction, or you have to extract certain most relevant features from this data, which is known as feature extraction, right. So, in this high dimensional data in machine learning applications, what one has to do is you have to take this high dimensional data and you have to reduce the dimension. Either you can think of it as a reduction in dimension. This is termed as dimensionality This is termed as dimensionality reduction, or you have to extract the relevant features from this. This is termed as the feature extraction. This is termed as the feature extraction step, right. For instance, let us take a look, let us take a simple visual example of that. I am going to illustrate a two-dimensional data. So, let us say you have two-dimensional data, for instance. So, data has a large spread. So, you can see this is your data has large spread, but if you look at this data along this direction, data has, this has the most spread along this direction, right. Most spread along this direction implies basically the largest variance, right, implies large variance. On the other hand, on this direction, if you look at this direction perpendicular, this has a smaller spread, implies this has small variance. So, essentially the data can be projected along this direction, right. The data can be projected along this direction. So, you can take, so what you can do is you can see your data has a large spread along a certain direction, while along the perpendicular direction the spread is smaller. So, you can take this data, project it along the direction which has, where it has a large spread, without using much of the energy, or while capturing all the relevant information in the data, right. Projection along those directions which have a large spread captures most of the energy or most of the relevant information without losing. So, you can reduce the dimensionality without losing the relevant information, right. So, that is the essential idea, right. So, essentially, what we mean is this dimensionality reduction, we reduce the dimension without losing. So, we want to reduce the dimension, but at the same time without losing, I hope you appreciate this aspect, without losing information, or you cannot say without losing information, while minimizing the loss of information, right. So, you are still capturing the maximum amount of energy that is there in the data. Now, the point is, how do you determine these directions with the largest variance? Now, the question that you want to ask is, how to determine the directions this direction with the largest variance. The answer to that, how to determine the directions with this largest variance, and this is essentially what is given as, so the principal, that is basically how do you determine these principal directions along which you can project the data to obtain the principal components. That is essentially what is given by the principal component analysis. So, that is the basis for the principal component analysis. So, the principal PCA gives the principal directions, remember, and now project along these principal directions, right. Project or data along principal directions to obtain along these principal directions to obtain the principal component. So, you project the data. So, once you determine the principal directions, right, once you determine these principal directions, the next step is to project the data, right, take the inner product along these principal directions to obtain the principal components of the data, and that results in dimensionality reduction. Okay. So, this can be and the interesting, so these have the largest variance, and these are the other interesting, these principal components are uncorrelated or orthogonal to each other, like what you have seen over here. These are perpendicular, these directions are perpendicular, right. So, you can see what you can see over here, that these directions are perpendicular. So, these principal components, these are, the property is these are uncorrelated, and we are going to see how that is going to be possible. These are uncorrelated or essentially orthogonal to each other. These principal components, these are uncorrelated or orthogonal to each other, right. How do we do that? Now, this can be, so PCA can be a, so what is the procedure for PCA? PCA technique, what is the procedure? So, consider the data set there are n points, each is of size m cross 1, where m is of course very large, that is why we want to compress it, or we want to do the dimensionality reduction or feature extraction. Okay. Now, so these are your n points, or you can call this as n vectors of dimension m, correct, n points, n data points, right, and each vector is of size m. Each is of size m. Now, first what we do is we remove the mean. So, we obtain, let us call this, I think it would be better if I call this as x tildes. So, let me call this x tilde 1, x tilde 2, x tilde n. Then you remove the mean to obtain xi bar equals x tilde I minus mu bar, where this is essentially what we call as the mean, or in this case we have to estimate the mean. So, this will be the sample mean, where mu bar equals 1 over n summation I equal to 1 to n xi, alright. So, this is essentially the sample mean of these points, right. So, this is essentially the sample mean this is essentially the sample mean of these points. Okay. Now, compute the covariance, estimate the covariance. How do we estimate the covariance? Now, you estimate the covariance as follows: R equals 1 over n minus 1 summation I equal to 1 to n x bar I transpose. This is the estimate of the covariance. This is your covariance estimate, and now you can see this is a positive semi semi-definite matrix. Remember, any covariance matrix is positive semi-definite. So, naturally the estimate also has to be positive semi-definite. So, the covariance estimate is a positive semi-definite, which implies eigenvalues are going to be greater than or equal to 0. Eigenvectors corresponding to the distinct eigenvalues are orthogonal. These are the important properties of PSD matrices, remember, alright. So, this implies eigenvalues, that is lambda I greater than or equal to 0, and eigenvectors for distinct eigenvalues for distinct eigenvectors for distinct eigenvalues, these are orthogonal. Okay. And now we have to find the direction of the principal. Now, the principal components can be found as follows: the directions of the principal components, or the principal directions. Let us the principal directions can now be found as follows, can be determined as follows. Let V1 bar be the direction of the largest principal component, or let V1 bar So, V1 bar is the direction of the largest principal component, which essentially implies this is the direction that has the largest variance, right, implies V1 bar is the direction corresponding to largest variance, or what we call the maximum spread. So, this is the direction corresponding to the largest variance or the maximum spread, right. So, how do we obtain this? First, let us find the projection. So, let us find, so you have V1 bar Hermitian x1 bar or xi bar this basically gives me, what does this give me, what am I achieving by doing this? This gives me the projection of xi bar along V1 bar. Now we compute the variance of this quantity, right? Now we have to evaluate the variance. Now the variance, as you know, can be evaluated as 1 over n summation I equal to 1 to n, 1 over n minus 1 I equal to 1 to n Vi bar Hermitian x bar I square, which is 1 over n minus 1 summation I equal to 1 to n Vm bar Hermitian xi bar, or we can call this as the transpose. Just to make things simple, let us make all these quantities real. Vi bar transpose xi bar into the transpose of this quantity. This is a scalar quantity, so I can write this as xi bar transpose V1 bar, and now this is going to be 1 over n minus 1 summation I equal to 1 to n V1 bar transpose xi bar transpose V1 bar, which is, now take the V1 bar outside, V1 bar transpose 1 over n minus 1, you can take this inside, summation I equal to 1 to n xi bar transpose times V1 bar. And now if you look at this, this is nothing but the covariance matrix, right? So V1 bar transpose, so variance corresponding to the principal component V1 bar, that is the principal direction of the principal component V1 bar, is given by V1 bar transpose R V1 bar, where R is the estimate of the covariance. Alright, so this is given by V1 bar transpose R V1 bar. Now let us also normalize the energy of the direction, right? Since we are considering a direction, we consider a unit norm vector. So the normalize, so when we consider the direction of, so let V1 bar denote the direction of the largest principal component, and we set norm V1 bar equal to 1. Okay, so this is a unit vector, and further so the direction is basically, we have the property norm V1 bar equal to 1. Basically this means that this is a unit vector. This implies V1 bar equals a unit vector, because if you scale it by alpha, any direction if you scale it by alpha, then the direction variance increases by alpha square. So to get a fair comparison of all the directions, we simply consider a unit vector. Otherwise, if you scale it arbitrarily, then the variance is also going to be large. It need not be that that is the particular principal component, the direction corresponding to the principal component, but essentially it might be the case that it just has a very large magnitude. All right. And therefore, now to maximize the variance, in order to maximize the variance, in order to maximize the variance, we have to have V1 bar transpose R V1 bar, which is the variance subject to the condition norm V1 bar equal to 1, and this is an optimization problem, or you can also say norm V1 bar square equal to 1, which implies V1 bar transpose V1 bar equal to 1. This is what we call as a constrained optimization problem. This is the objective, this is the objective, and this is the constraint. And therefore, this is what we call as a constrained optimization problem. So, this maximize V1 bar transpose R V1 bar subject to the constraint norm V1 bar square equal to 1. This is essentially what we are calling as a constrained and we can solve this using the KKT condition. So, this first of all we have the objective V bar transpose lambda V bar transpose R V1 bar plus lambda times 1 minus V1 bar transpose V1 bar. In fact, you can write this constraint as V1 bar transpose V1 bar equal to 1. This is basically what we term as the Lagrange multiplier. This is the Lagrangian, this is basically what we term as the, this is from the theory of convex optimization, and now you find the gradient. So, this is your Lagrangian, and now you find the gradient of the Lagrangian, right. So, this is your gradient, right. I am just giving you the key steps because this is a very interesting problem that arises frequently, which basically is simply the partial of f with respect to every element of the vector, dou f by dou v bar 1 2, dou f by dou v bar 1, dou f by dou v bar 1, I think this is m dimensional, right. So, dou f by dou v bar 1 m, alright. So, we are taking the derivative with respect to each of these elements, and this can be shown to be given by the gradient with respect to V1 bar of V1 bar transpose R V1 bar plus lambda 1 minus V1 bar transpose V1 bar, which is essentially you can show to, which you can show to be 2 R V1 bar minus 2 lambda V1 bar. And now to maximize this, to find the stationary point, we set it equal to 0. We set the gradient with respect to V bar equal to 0, just like you set the derivative for a single dimensional function to find the maximum or minimum. You set the gradient equal to 0. So, you set it equal to 0 to find the, this is the KKT condition, okay, Karush-Kuhn-Tucker condition. So, this is the KKT condition for extremum. Of course, this is a convex, of course, you can show that this will have a maximum, and therefore, this is the V1 bar transpose R V1, and this essentially implies that now what this implies is that R V1 bar equal to lambda V1 bar, which essentially implies that V1 bar is, if you can see, this is nothing but exactly the definition of an eigenvalue, that is R V1 bar equal to lambda times V1 bar. So, V1 bar is an eigenvector of R corresponding to the eigenvalue lambda. So, V1 bar is an eigenvector of R corresponding to eigenvalue lambda, and further V1 bar transpose R V1, which is V1 bar, which is the variance, is given as, now R V1 bar equal to lambda V1 bar. So, this is V1 bar transpose lambda V1 bar, which is lambda V1 bar transpose V1 bar, which is equal to lambda times norm V1 bar square. So, this is lambda times norm V1 bar square, and norm V1 bar square is 1. So, this is lambda. So, to maximize variance, it is very obvious that we need to maximize lambda, that is to maximize the variance of this, right. To maximize the spread along this principal component, you have to maximize the lambda, and therefore V1 bar is the eigenvector of the covariance matrix corresponding to the largest eigenvalue lambda. That is the interesting result. So, the direction of the principal component, the largest principal component, is basically the eigenvector of the covariance matrix corresponding to the largest eigenvalue. So, that is the very interesting result. So, V1 bar equal to eigenvector of R corresponding eigenvector or R corresponding, thus the directions of the, so if you want to have principal largest components, thus if you want to extract P features, directions of the P principal components are, essentially call them as V1 bar, V2 bar, Vp bar, which are nothing but the eigenvectors of R corresponding to the P largest eigenvalues. So, these are the eigenvectors of R corresponding to the P, these are the eigenvectors of R corresponding to the corresponding to the P largest eigenvalues. That is, if you call them lambda 1, lambda 2, lambda p, the corresponding eigenvectors V1 bar, V2 bar, Vp are, these are the directions of the principal components. And remember, the eigenvectors corresponding to distinct eigenvalues are orthogonal, right. So, these are, you can find these vectors such that these are orthogonal, right. So, these are orthogonal because recall R is PSD. So, this implies the projections are going to be uncorrelated, right. When you take the projections along these orthogonal, so the projections are going to be uncorrelated. So, this implies This implies that the projections are going to be uncorrelated. And now the principal components of the vector xi bar can be found as, so principal components of xi bar can be found as V1 bar transpose xi bar, V2 bar transpose xi bar, and so on and so forth, Vp bar transpose xi bar, which you can write as in the compact form. We can write this as the matrix V1 bar transpose, V2 bar transpose, Vp bar transpose times xi bar, which can now write as the matrix V transpose xi bar, where V is the matrix containing the eigenvectors V equal to V1 bar, V2 bar, Vp bar. So this will be your, each is a vector of size m. So this will be your I would like to say each is a vector of size m. So this would be a vector of, this would be an m cross p matrix. Okay, this would be an m cross p matrix. And now the principal components of the entire data set. So the principal components of the data set. So this is basically your dimensionality reduced vector. So if you look at this V transpose xi, you can call that as xi check. So this will be a p cross 1 vector. This will be a p cross 1 vector because this is your m cross 1, and p can be much smaller. That is the whole point of dimensionality reduction. P can be much smaller reduction. So this is basically the dimensionality reduction. This is basically where the dimensionality reduction is arising, because you are choosing a much smaller number of principal components, that is eigenvectors V1 bar, V2 bar, Vp bar, such that they capture a significant fraction of the energy that is there in the data set x1 bar, x2 bar up to xn bar. Alright. So, and the principal components of the entire data set. So, principal components of the data set are obtained as So the principal components of the data set, these are given as that is you have V bar or V transpose into x1 bar, x2 bar, so on up to xn bar, which essentially gives you the matrix, this gives you the matrix. What does this give you? This gives you the matrix x1 check, x2 check, xn check. So this is, we started with this m cross n matrix, and this is the extracted features. These are the p cross n. This is the reduced dimension, or this is basically the dimensionality reduction. So this is given by the, so these are what we are calling as the principal components of the These are what we are calling as the principal components of the data set. So, this is basically your dimensionality reduction or feature extraction. This process is basically your feature extraction or basically your dimensionality reduction. Or basically your, this is basically your feature extraction or dimensionality reduction. All right. So, this is essentially the concept of principal component analysis that is used extensively in machine learning. In ML, as we already said, to take large dimensional data and compress it into data of much smaller dimension, that is to reduce the dimensionality of large dimensional data. All right, and this step can also be termed as feature extraction. All right, so we will stop here, right, and I hope you have enjoyed this and application. This explains in a very practical way what I mean, this explains a very interesting practical application, some of the concepts that we have learned so far, that is positive semi-definite matrices, covariance matrices, eigenvalues, eigenvectors and so on. So, these, as I have already said, these arise, the concept of positive semi-definite matrices, eigenvalues, eigenvectors, these arise very frequently in practice. So, let us stop here and continue in the subsequent lectures. Thank you very much.